Hey, welcome. Nice to be here. Nice to see you. My name is Rene Schulte. I'm Director of Immersive Experiences at IdentityMine. I'm also Microsoft MVP for Windows development. And I have a background in computer graphics, virtual reality, and augmented reality, actually since a couple of years. Just like 2 weeks ago, I think it was, I had an anniversary when I was porting one of my open source projects over to Windows Phone Mango. Does anyone remember Windows Phone Mango? Yeah, good. You're my man. So this was this kind of when they added like camera access APIs. So I had this AR toolkit port I was doing since quite a few years. So like I said, I have this background in VR, AR since many years, and that's why I'm here today to talk about HoloLens development with you. So first I want to explain some terms which are often mixed up, like what is VR, what is AR, what is MR. Just a few minutes. Then we will talk about HoloLens, of course, and how you can develop for it, and we will do a quick demo. So I will show you step by step how you can develop your first HoloLens application with Unity. And at the end, we will also spend a good time talking about best practices and some learnings we got through doing HoloLens development since last year, actually. So let's, a few words about the company I work for. IdentityMine is headquartered in Seattle. I actually work out from Dresden in Germany. And IdentityMine has always been at the bleeding edge of technology. So we have been developing for big multi-touch devices, Pixel Sense, tables, Xbox 360, Xbox One. We actually also have real-world deployment of a Kinect for Windows app out there. And we were also invited by Microsoft to be part of an early program for HoloLens development. And yeah, that's what I want to share with you today, some of the learnings we got there. So let's roll a quick video about the company. It's just 1 minute. But it's actually a nice one because it shows you some of the HoloLens stuff we built. Okay, enough of the marketing. Let's talk about some stuff. Most of you are already familiar with those terms, but some people might not, so let's stick with me for a few minutes just to set some terms straight. So virtual reality, what is that? Virtual reality is a fully immersive multimedia solution, which means you're fully inside your virtual world. You don't see the outside world anymore. And this has been around since actually many years. Think about flight simulators and that kind of stuff. It's around since many decades, actually. But now we have the devices like on the low-end spectrum, we have Google Cardboard. On the high-end spectrum, devices like the Oculus Rift, which have a huge computing power, and they provide a very good quality for a reasonable price. And when I say quality, I especially mean low latency, because the main challenge with VR is, of course, you want to have a good realistic rendering, but also you need to pay attention to a very short latency. So everything that's taking longer than 3 milliseconds from a feedback, that can actually make your users sick, right? They can throw up, they can get headaches, and so on. So you need to be very good with latency, but on the other hand, you also want to have a very good rendering. So that's always a challenge, right? And of course, those devices, they're very good stereoscopic displays, but we humans don't just have eyes, right? We have ears, we have hands, so haptic feedback is something you can implement, or spatial sound is very important. And I heard there are even experiments with virtual smell, which could be fun, but could be pretty awkward as well. I'm sure some of you will build the first VR thought app. So that could be something. This is your next journey, basically. No. So what is AR and MR on the other hand? Augmented reality and mixed reality are not fully immersive, right? So not fully inside the virtual world, you still see the real world around you. And those real world scenarios are augmented with virtual objects. And Microsoft built a device called the HoloLens, and I have one with me here. And we will talk about this in a second. And Microsoft uses the terminology mixed reality for the HoloLens. although it's actually also augmented reality. So it's kind of an umbrella term, and everyone seems to use the different word for mixed reality. Everyone seems to use it for different use cases. So Microsoft uses mixed reality to kind of diversify from other augmented reality applications we have or devices. And usually those AR apps, you probably have a smartphone or kind of a tablet, you have this AR apps. So they scan the room, basically, they use the camera stream, and that is analyzed. And then you see the camera stream, so you see the real world on your device's display, right? You don't see it with your own eyes, you see it through another screen. But with the HoloLens, you have that transparent see-through lenses, so you can see the real world with your own eyes and not through another screen, which is, by the way, of course, monoscopic, right? It's a Cyclops. It just has one camera. But with the HoloLens, you have those nice see-through lenses, so you see the real world with your own eyes, and you don't also have the latency. Challenges with AR and MR in general is, of course, you don't just need to generate some virtual objects, you also, of course, need to analyze the real world. You need to find some markers, or like the HoloLens does, it does a spatial mapping of the room. So this is, of course, taking even more resources. This is taking more computing power, which is, of course, a limited budget, right? So even more challenging than VR, actually. And of course, you want to seamlessly merge your real and your virtual world, which is one thing you really want to do to make a nice augmented mixed reality experience. So let's talk about the HoloLens. The HoloLens is a head-mounted device from Microsoft, and I have one here with me. This is the current developer edition. You can, if you're lucky, you can get it somehow. And it has a bunch of sensors in here. So it has, first of all, those cameras here. Those are environmental cameras. They basically scan the environment and do the surface reconstruction or spatial mapping. So the HoloLens can understand the room. It has this spatial awareness. It also has an RGB camera, a depth camera, microphone array for speech recognition. Does it very well. And of course, a rotational sensor, which is called IMU, Inertial Measurement Unit. And all of that is in the device, right? So this is basically not just a head-mounted display, this is a computer. So all the computing is done on device. It has a CPU, it has a GPU, and a new coprocessor Microsoft calls the Holographic Processing Unit, the HPU. And the HPU is basically doing the spatial mapping, gesture recognition, speech recognition, and so on. It also has 2 gigs of RAM, it has storage, yeah, and batteries. And it can do this for a couple of hours, actually, which even after working once with that device, it's still super impressive what it can actually do, and even for a couple of hours with battery lives. And it runs Windows 10, so it's basically a Windows 10 device, which means you can also install your Windows Store application, like Microsoft Edge browser. Don't open Edge browser tabs anymore, you pin them to your wall, right? Those kind of things, since it's a Windows 10 device. So let's talk about input and output with the HoloLens. And the HoloLens uses an input paradigm called GGV, which stands for gaze, gesture, and voice. So if I wear the device like this, and I rotate my head, this is how I can set the gaze vector. This is how I can set basically a ray where I'm looking at, right? So I rotate my head, and this is where I'm gazing. And this basically sets your interaction focus. This is, if you'll think in the desktop world, this is like your mouse move, right? And then you can trigger a couple of gestures. And one important one is the air tap. So you hold your index finger up and tap down. And this is basically triggering, if you're thinking desktop world, the mouse click. So think about gazing, setting the interaction focus, and air tap to trigger the actual action. There are a few more gestures. You can also do a tap and hold for scrolling or something like that. And also a built-in gesture is like the bloom gesture. This is how you can bring up the start menu. And you notice it's quite limited input. So speech is a very important input paradigm with the HoloLens, and it does a very good job. It even works better than with Xbox One. The microphone area sitting directly on top of your head works very well and very natural for users. So voice input and speech commands is a good way to control your applications or your games. Yeah, it has those 2 see-through lenses I mentioned. And those are not just simple flat lenses, they're actually multi-layered glasses. So the RGB signal basically is split up into each channel, and this is fed into each layer. And each eye can basically be filled with 1 megapixel. So the resolution is 1 megapixel per screen. Yeah, and spatial sound. So the HoloLens has those small speakers sitting above your ears, and I will show you a bit about it in a later slide. And spatial sound is providing a very good spatial and immersive feeling for the user. So how can you develop for the HoloLens, right? What can you do? So first of all, you can use Direct3D. It's Direct3D 11, so you can use C++ or even a SharpDX and C#. Or you can use Unity. And we are at Unite, so we are using Unity, right? And Unity, as you know, it's not just a 2D or 3D game engine. You can actually also build applications with it. And you have all that cool and amazing stuff built in, like Enlighten, physics, and so on. So you get a bunch of stuff for low cost or for free, right? And you have this nice, high-efficient workflow, easy to work. We have like 24 platforms, like we learned yesterday. It's growing and growing every year. And yeah, you have VR support built in. So Oculus Rift is built in. You don't need to install an extra SDK anymore. And also PlayStation VR, I think. And of course, HoloLens. So there's a HoloLens built into the Spatial Unity build, so you don't need to install a separate plugin. You install the HoloLens SDK and that Spatial Unity build, and then you can get started. And HoloLens, Unity is first-class citizen for HoloLens development, that's for sure. So if you look at the tutorials Microsoft puts out, they're all based on Unity. Actually, also a couple of the apps and games you find in the Windows Store from Microsoft, a few of them are built with Unity. And it's pretty impressive how polished and how nice they are. So Unity is a safe bet for HoloLens, that's for sure. Yeah, and it will still be free for personal use, right? That's good. So let's talk about. No, don't stop. I will stop talking now. I will do some demo. So let's do some actually development and build some stuff. So what we will do is we will start with a fresh new Unity scene, and I will show you what you need to set up, what you need to configure in order to deploy it to the HoloLens. And then we will implement also the basic input paradigms I just showed you. We will have gazing, gestures, speech commands, and spatial mapping. So like I said, the amazing thing with the HoloLens is it understands the room. So it can scan the room, and you can use that basically also as a mesh collider. So what we will build is just a simple game, if you will, just a plane. We will stack some cubes on top of that, add rigid body physics, and then we can shoot spheres from our camera, from our head onto those, and they will bounce off. So let's get to Unity, and let's build it. So I have a fresh new scene here, right? And first thing we need to set up is the main camera. Because when you start a fresh new Unity scene, you'll have those values by default. But the HoloLens maps, when the user walks around, it maps that to the position of your main camera, and also the head rotation is mapped to the rotation of your main camera. So we want to avoid having an offset here. So first thing we need to do is reset the position to be 0, 0, 0. So we have this. Another thing we need to set up as a solid color black as clearing, because the HoloLens uses additive blending. So the virtual objects are blended in additively, which means black is transparent. So we clear to transparent basically each frame, but we can just use black and that as clearing color. Another thing we will set up is the near clipping plane. So we will set it to 50 centimeters. So it's recommended to set it to 50 or 80 centimeters, because everything that gets closer, the virtual objects that get closer to the viewer, to the user, can make the user's eyes get crossed. And that's very uncomfortable, so make sure to clip it at a certain distance. You can experiment with what's a good value. 50 or 80 centimeters works pretty well. And for clipping plane, let's reduce it to 10 meters. That's just good enough. Another thing we need to set up is the actually player settings. So let's open the player settings for Windows Store applications. Because what the HoloLens app in the end is, it's a UWP, Universal Windows Platform, or Windows Store application. So we need to configure that. And we will set, under other settings, we are supported. We will check the checkbox here. And this will include the Windows Holographic SDK in our project. OK, so if you have done WSA or UWP apps before, you also know that you need to find some capabilities if you want to use certain features in your application. We will use the emulator, so we will enable Internet client, although our demo won't connect to the Internet, but the emulator connects to the hosting operating system, so that's a good one. Also, we will enable microphone, so we want to use speech recognition and spatial perception, because we want to use the spatial mapping feature of that. Otherwise, if we would not check those checkboxes, we would get an exception at runtime that the capability is not enabled. Good, that's what we need to set up here. Let's build actually some content for our scene. Like I said, we will go with a plane and some cubes. And what I usually do is I create an empty game object, which I call container, where I can group all those objects together in a nice way. And we will set this container a bit further away from the camera. So we will go like 50 centimeters lower than the camera and 2 meters in front of the camera. And this is usually a good idea, because when you launch the application, that you actually see the content a bit in front of the user, like 2 meters away, is a good idea to place them there. But of course, it depends how large those objects are, and you need to experiment what works for your use case. OK, so let's add a plane into that container. It's a bit large, so let's reduce the size here. And let's go with that size. Another thing we want to do, let's add a material, because we want to have a nicer material. And since we're good citizens, we are creating a folder for our assets. Materials. OK, so let's add a simple material. Well, we make a green field, so let's call it green. Change the color, whatever. Doesn't matter that much. And there we go, our green plane. OK, so let's add some cubes on top of the plane. Also a bit on the larger side, so make them smaller. And raise them a bit. Oh, and we want to use rigid body physics, so let's add the rigid body physics component. And that cube looks nice, so let's duplicate it. And oops. And build our small stack of cubes, yeah, like this. And that guy. OK, let's see if it works, if our rigid body physics work. Just pressing the play button to see if everything is nicely hooked up. That looks good. OK, so we have our basic scene set up. Let's add some actual functionality. Let's do some scripts, and I will show you what you need to implement in order to use some HoloLens-specific APIs. And another folder, scripts, and let's add a C# script in there. And since we are shooting spheres from the camera, like I said, we will call it the cannon behavior, and I will attach that cannon to the camera. Right? So the camera is the user's head. You will shoot spheres from the head, basically. Good. Let's open that script file. And yeah, and I won't apologize for doing any coding, right? So we're doing some live coding here, and we don't have to watch me typing. I prepared some code snippets, but well, we want to see some coding, right? Are there any developers in the audience and others? So what is the developers? Awesome. Artists? That's fine. That's great. You will learn some stuff. Don't worry, and we'll keep it in a way that I think everyone can understand, even if you're not a hardcore developer. So that's great. Let's remove the stuff Unity generates for us. And like I said, I prepared some code snippets, and I plugged them just in here, and we will talk through them. That's better than watching me typing, because I make typos all the time. OK, so here is one specific API. It's called Gesture Recognizer. And like the name implies, this is used. This is filled basically by the HoloLens SDK and provides the gestures, or a way to access the gestures. And it has a couple of events. One is the tapped event. So this event is triggered basically when the user does a tap, right? Could be a double tap, or single tap, or triple tap, whatever. And then we also need to tell what kind of gestures we're interested in. So for our demo, we're just using a single L tap, so one tap is fine. And then we call start capturing gestures, so you can start and stop gesture recognition however you want. OK, so let's add the event handler when the user basically L taps. This is the event handler that is called, like you can see here. And this is just calling one single method, which is called shoot. So let's see what we're doing when the user L taps. We will create a sphere as a game object. And since we're shooting them from the camera, I thought those are like your eyeballs. Shooting eyeballs in the scene, because that is fun. We will reduce the size of it to make it not that large. Add a rigid body component, give it a certain mass, and set the initial position to the camera position. So we attach the script to our camera, which means the transform is the camera transform. And we will start there from the camera transform position, and we give it a force. We say in the direction the user is looking at, transform forward, the user's forward vector, and multiply it with a constant. So we give it a certain impulse. And we will use this public field so we can change it from Unity Inspector and give it an impulse of 300 Newton. OK, let's save it. Switch back to Unity. Our script is updated. You can see it here. And let's deploy it for the HoloLens. So we go to File, Build Settings. We have to select Windows Store. Like I said, it's a UWP, it's a Windows Store application, and it's a Windows 10 device, so Universal Windows 10, and Direct 3D, because we want to have a 3D rendering. Then you click the Build button. You need to select the folder. You're all familiar with that, so let's build it out. And what it basically does now, it generates a new Visual Studio solution, not the one we use in the editor, because as you know, there are two different Mono runtime, there are two different .NET runtimes. The editor uses Mono, UWP uses .NET Core, and so we get our build output is basically a fresh UWP solution, which we can open with Visual Studio and deploy that to the device or the emulator. So it's done now. I did this before and open it up, so we just need to reload it here. And then we can launch our applications. So I usually select Release. The HoloLens is a 32-bit device, so x86. And then you can select your deployment target. So I could say device, if I had the device connected via USB. Or I could also say remote machine, if I would have connected it via IP address. So I could deploy over the air, basically. And for this first one, we will use the emulator, because I want to show you the emulator for a second. And I also launched that one before. The emulator, this is the emulator, basically. Yeah. And you can basically also simulate gazing. So it's the left mouse button down, and you rotate the mouse. That's how you can simulate gazing. And right mouse button down is giving an air tap. And this is all for free and integrated in the SDK. So this is our scene. We loaded it, and now we can air tap and shoot those spheres in the scene, right? That's not very spectacular. But you see an issue. I don't know where I'm looking at. I don't know where I'm aiming, right? You don't see the gaze cursor. You have no indication of gazing. So it's hard to aim, and I often miss those. So let's fix it. Let's add a gaze cursor to our scene. Stop the emulator. Go back to our script. And we will do this, whatever, format it like you want. And we will add a gaze cursor. So the gaze cursor is, in our script is just a reference to another game object. So we will create a new game object, which we will use as a gaze indicator, kind of like a cross you can think of where you can aim at certain targets. Let's pull in an update method. So what I do here is, in the update method, I do an raycast all, which you probably should not do in an update method. But for the sake of the demo, to keep it simple, I'm doing it here, right? You would probably do in raycast all. You could implement your own pointer input module and do this kind of stuff, or somehow cache the raycast results and not do it every frame. That's not what you should do in a real application, but as I said, for our demo, we're just doing it like this so I can show it to you in an easier way. Okay, we're doing raycast all, camera perspective, from the camera position, shooting out rays into the scene, and those rays hit certain objects, and then we sorted them by distance, and the closest hit objects, that's what we're interested in, that's our raycast hit we want to use. And we apply the point of the raycast hit as a transform position to the gaze cursor, so we position it where our object is, and then we will also orient it correctly to the surface of the object using the raycast hit normal. Good. So let's build the actual gaze cursor in our Unity. So I will add a new object, and we'll just go with a smaller cube as our gaze cursor. And let's reduce the size of it to maybe like this, and make it a bit flat. So this is our gaze cursor. Let's remove the box collider, because we don't want to have any physics collisions here. And this would be shown on top of the objects. Of course, we would not see much if we would just use the default material. So let's give it a different material, like red, and pick a red one. And this will be our gaze cursor, right? We will shoot this on top, but we need to hook it up, of course. So let's connect it here, that our script has the reference. So we have gazing, we have gesture, air tap gesture, and before we deploy it again, I want to save some time for deployment, of course. So let's add something else. Let's add spatial mapping to it. And spatial mapping is actually quite complex to implement, so you have to write a couple of lines of code. But the good news is, someone else did it already. And actually, Microsoft did this. And Microsoft provided a GitHub project, an open source project called HoloToolkit. And this is a bunch of scripts and prefabs and shaders and materials implemented, which help us. So they have like a spatial mapping collider, which I I just made a quick package where I only have those features what I'm interested in for this demo. So let's import those into our scene, and we will talk about those scripts in a second. I have a prefab for the spatial mapping, so I just add our prefab, and this is just an empty game object, and it has two scripts which come from the Holo toolkit, like I mentioned. The first one is the spatial mapping collider, and what it internally does is, of course, it builds a mesh collider based on the spatial mapping data it gets from the HoloLens. So the HoloLens scans the room, as I mentioned. And we could define a few things. So we could set the sphere radius. So I could say I want to have a bounding box around me or a sphere, and I can say this is a sphere, and everything that's 5 meters around me, I'm interested in that kind of stuff. So I'm setting 5 meters here. Then I can also set the level of detail. So of course, this is always a performance and detail trade-off. So low performance, high detail, higher detail, lower performance. So let's go with low, that's fine. And we can also say time between updates here. This is in seconds. So I could say how often this spatial mesh is updated. And this means that's 2.5 seconds. So if a person's walking by fast, this won't get recognized. But if I would place a table in here and wait a few seconds, the mesh will be updated. Yeah, and you also can define the physics material for those properties like friction and so on. And you also have the spatial mapping renderer script from the Holo toolkit. It's pretty similar like the collider one, but you can define a material here. So you could say, I want to visualize actually a spatial map. Or you could also say, I just want to use it for occlusion. So I just want to occlude my virtual objects with the real world, right? For our demo, we will use a wireframe material to visualize it. So it's just like a simple wireframe. We could also use an occlusion material with an occlusion shader, which is just, you see it, it's just writing to the depth buffer to make sure the virtual objects are occluded. Good. So we have spatial mapping, we have gazing, we have gestures. Let's add also speech commands. And for this, we will write a new script, which I call speech handler. So let's add this one. Speech handler. OK. And let's add some code to it. There it is. Let's clear that stuff. And let's talk about the code a bit. So what I have here is the speech handler. And this one has a bunch of properties implemented. So first one is we create a new instance of keyword recognizer, so which is pretty similar to the gesture recognizer, the gesture recognizer. But in our case, it takes an array of strings. So I could just define strings as speech command, which is pretty amazing. You see that? I just have some strings up here, which I pass in as an array item. And those are just simple C# strings. And the HoloLens basically can recognize those and can even provide those speech commands without any thought or assistance. So if you have done speech commands on other platforms, you have to define an XML file with a grammar and kind of stuff. So this is really simple, just strings. And once that is recognized, the phrase is recognized, it's triggering an event handler. And that event handler here gives us the arguments, and the arguments contains the text that was recognized. It could also give us the confidence, so how we don't get suggestions. So how sure it is what kind of stuff was provided. And then we compare those speech commands with our actually defined speech commands up here. And then we can say certain commands. So let's set the plane deactivated when the user says hide plane. Then we will deactivate the plane. When the user says shoot, we will shoot the cannon, or reset scene, we'll reload basically the scene. We also need, of course, to enable to copy the right namespace. So hopefully it will get recognized. And yeah, that's it. We saved it. So let's we forgot the right namespace here. Okay. Yeah, whatever it is. Well, somehow Visual Studio threw up on me. I don't know. Anyway, let's do it differently. So we have speech commands implemented. What we would do now, we would add this script to our main camera. And we would plug in those elements, right? So, but instead of showing it to you in the emulator again, I will show it to you in the actual HoloLens device. So like I said, we have gestures, we have gazing, we have speech commands, and we also have spatial mapping. So there's a nice little tool from Microsoft. It's a universal Windows platform application, so it also runs on mobile. And this allows me to show you a live stream from the actual HoloLens so you can see what I'm seeing. Otherwise, it would be pretty boring, I guess. Well, let me try to put it on. Adjust the head strap a bit so it fits nicely. Okay, that's good. And let's start the live stream. Okay, cross the fingers. So I bring up the start menu, and now we will launch the application we have just been building. It looks a bit different than what we have built, but it's pretty similar to the one I have shown you. And you will get all the source code from the demo on GitHub. I will share a link with you, and then you can see all the stuff from GitHub. So what we see is our three boxes here, and you also see the gaze cursor. I used a different one. I used like 2 small cubes, like a cross. And so I can gaze at the objects, and I see where I'm looking at, basically. Well, and then I can trigger an AirTab gesture. And since we're in the Netherlands, there's a famous... who's from the Netherlands? Just a few. OK, so you can tell the rest of the audience what a bitterballen is, right? It's a famous dish in the Netherlands. And, well, so that's a famous dish in the Netherlands, the bitterballen. So instead of shooting just simple spheres in our demo, we will shoot bitterballen. So let's shoot some bitterballen, right? And you see that? Those objects are bouncing off here in the real world. So I can shoot those guys. Oh, and there's also myself. I was yesterday at the Intel booth. They had this nice 3D camera where you can scan yourself. So of course I had to put myself into as a hologram, and I can shoot at myself. Well, the stream is frozen again. I don't know. Anyway, so, but you saw it, right? The objects, you see them, the virtual objects, the bitterballen, you can all eat some of those, but they won't be very tasty. They are all virtual objects which are bouncing off in the real world, right? So this is the power of the HoloLens. It does the spatial mapping. It understands the room, so you can let your virtual objects interact with the real world around you. Pretty amazing, if you ask me. So, let's close this guy. Switch back to the presentation. Yeah, and since I know the Wi-Fi can be spotty, I prepared something. So this is at my house at home. And like I said, we're shooting eyeballs. So I'm shooting eyeballs down the stairs at my house. And you can see those objects, those virtual objects, also interact. So you have a different setting here. In this case, you have the stairs. Voice commands works. And I also have spatial sound implemented. So we didn't do this in the demo, but on the GitHub project I share with you, you can get all of that. Right? And you see how nicely they roll down the stairs and how the spatial mapping works well. OK, so shooting eyeballs or bitterballen and stuff is fun, right? But it's a really small niche if you want to make some money, I guess. So let's talk about some real-world applications we have been building. And we had quite a few client engagements by now. One of them was, for example, we engaged with a museum, so we tried out some different things, and we just figured, let's put some dinosaurs as holograms into our office. And this is like also one of those magic moments, because it allows you to see them at the real-world scale, right? You see them, how big they are in the real world, actually. And this is really nice with dinosaurs, because you cannot see them in the real world. But with hologram, you can see them at the real-world scale. We also did some stuff for automotive industry, construction, plane maintenance, and a few other things. Another one I want to mention is HoloFlight. This is an application that kept me busy the last couple of months. And this is basically a real-time flight data visualization. So we're taking real flight data and visualize it in holograms. Right now, what you see mostly with those air traffic controllers, they look at the flat radar panel, a 2D screen, right? But planes and flights are actually flying in 3D. They have an altitude. So it makes sense to visualize them in 3D, and it's even cooler to visualize them as holograms, so you get the stereoscopic information, and you see them, how they relate to one and each other. You know, how big they are, and how fast, and so on. It's so much more information you can actually see there. I want to show you a quick video. It's just 1 minute, so you can see the features that are inside HoloFlight. And this will give us a chance to talk about the challenges and the solutions, what we came up with for the application, and a few of the other learnings I want to share with you. So this is HoloFlight, and you can see the Hawaiian Islands here, right? This is the Hawaiian Islands real-world topographic data we actually use from the Bing Maps API. And you can gaze at planes, you can enable them, you can see the plane information like call sign, altitude, speed, and much more. You can even hear air traffic control conversations as spatial sound. You can also see airport information, so you can see like the turning wind speed, temperature dew point. And you can place those information panels in the room. So we use a spatial mapping of the HoloLens to basically let the user lay out the workspace, right? You can place those information panels. We also support different level of details, so you can zoom into a higher detailed mesh showing just one island. And we're using real-time data, like I said, but we can also use cached data from our own Azure backend. This allows us to play back the flight data at different times, at different speed. So you can see if we play it faster and let those trails stick, you can visualize the trails very nicely, and you see the usual flight routes. So this is another informational value you can get, which you don't see usually. So what are the challenges when we implemented that? First of all, when you visualize flight data, you run also in a bunch of issues, because usually it's meant to be visualized in 2D, right? But visualizing in 3D also adds another dimension of errors, basically. You need to be careful to not polluting the holographic frame, right? You have a limited frame, you have a certain size of a frame, and you want to show a lot of flight information. Flight information is very dense, lots of stuff, but you need to be careful that you're not putting too much stuff in front of the user. And we want to use the spatial mapping, because the spatial mapping is really one of those unique features of the HoloLens. It's really amazing, and of course you want to use that. You make use of that, and you have seen how we do that. And we will talk also a bit more detail in the next few slides. When you gaze at objects, like I said, you interact with them. It can be hard to gaze at those tiny planes, so we had to find a solution for this. And of course, we want to make an awesome immersive experience, which is also including spatial sound, because this is really nice. So what we did? Well, first of all, you need to find the right flight data. There are a bunch of providers out there. We found a good partner that provides us the flight data in a nice REST-based web API as JSON, which is easy to parse. Everyone can do that. But then we noticed there are a bunch of errors, which you don't see in 2D. For example, we had some crazy altitude drops, which don't happen that often in the real world, right? Otherwise, no one would fly anymore, I guess. So we had to fix those. So you have two choices. You do it offline, cache the data, fix it up, or you do it online in real time. So we decided to do it in real time. So we spent quite some time to develop some algorithms to filter, to validate, and to make the data nicer so that you don't see those issues. Then, of course, you need to map it. So you get geographical coordinates. Then you need to map it to an unwrapped planar rendering, basically. Altitude mapping is also interesting, because we have like 30 to 45,000 feet of altitude information. And if we would just map that linearly into the rendering space, we would waste a lot of interesting rendering space with a lot of uninteresting flight information. Because the most interesting flight information is the one that's lower to the ground, like the first 3,000 to 5,000 feet. So we do nonlinear mapping, basically. Right speed, like I mentioned, so we want to visualize at the right speed, and also the right size, level of detail is important. So let's talk about the UI a bit. Let's talk about not polluting the holographic frame. So we spent a couple of iterations to actually visualize that flight information. And that's the first one. That's my fault. It looks super ugly, right? Developer UI, you don't want to do that. So next iteration I came up with was in-place billboards. So you could gaze at the plane and see the flight information, air tab to make it sticky. But you see the issues when you have multiple planes flying. You run quickly into some overdrawing, into some overlay issues, which are not nice. So the next iteration was a central curved screen UI. So we had a curved screen, which is fitting nice with also with a human head, right? It's also curved, and you see all those curved TVs. But then we wanted to show more information in it. We wanted to show a list of flights, wanted to show weather information. So this thing kept on growing, and as you can see in the screenshot, it wasn't fitting in the holographic frame so nice. So what we did is we split those up into independent panels, and then we polished it to what you have seen in the video. And those can be placed independently in the room. So you can take those, put them on the wall, and lay out your workspace as a user and make yourself comfortable, and you can decide where to place the stuff and at what distance and how much you want to see at any time. Yeah, size matters also for raycasting. And as you have seen in the videos, those planes can become quite small because we are using real-world scale. So it can be hard to gaze at them, it can be hard to select at them when we would just use the mesh collider of the plane, right? The gaze ray would often miss. So what we do instead, we use a sphere collider, actually, and we can also dynamically adapt the size. So if the user is stepping a bit further away, we can make it larger to a certain amount, of course. And if you're getting closer, you can make it smaller, and then also at a certain distance just swap to the actually mesh collider of the plane. So dynamically adapting it, basically. And of course, this is also a good performance trick, because ray to sphere test is very easy, cheap to compute. Cool, spatial sound. Well, you see it on the slide here. There's some experiments with some weird spatial sound helmets. I'm sure this thing provides a super immersive spatial sound, but it's also, I guess, a bit heavy on the head, right? So, and you don't need it, because the HoloLens has those amazing little speakers on the side, as you can see on the slide, or here on the device, right? You have those small little red speakers here. And of course, they don't provide a super bass sound, but they do a very good job at providing you the spatial information. So you know immediately where to turn your head. You know immediately where the sound is coming from. And in HoloFlight, we use it for this.
Seabird 182 Heavy, right Mike Alpha, right Bravo, then Papa.
So we use it to play back air traffic control conversations. And we play those back at the plane position in 3D space, right? So it's not just adding value from the ATC conversation itself, but it also gives the user a spatial hint where to turn the head. Because as you can imagine, you don't see all the holograms all the time. So when you walk away, when you walk around, this terrain might be here, the plane might be flying there. So I might be searching, where I can look. You can do some visual hints, but spatial sound is also amazing for doing that kind of spatial hint to the user where to turn the head. Because when you hear the sound, you know immediately where to turn your head. They did a very good job at implementing this functionality. And if you have a use case in your application, make sure to use spatial sound. It's really the topping on the cake, if you will. There are some further best practices. So first of all, you want to use fading and transitions. Because in the real world, objects don't just appear or disappear, right? Maybe ghosts if you believe in such stuff. But virtual objects, you can enable and disable them. So it's easy to bring them in and out. But of course, you want to merge your virtual objects into the real world. So you want that your virtual objects behave like real world objects. So they should either move in slowly, grow in size, shrink in size, some kind of transition. I have 3 short clips here where I want to visualize you the differences in doing that. And we see all the Hawaiian Islands here. And if we want to do a transition and just swap to another mesh with one island, it's very awkward, right? You see all the islands of Hawaii, and we want to just zoom into one, and it's not nice. It's not working well. It's not good for the user. So what you could do instead is a cross-fading, alpha blending between the 2 meshes. It's better, but you don't know the context, right? So the user doesn't know which island did I actually zoom in. Where am I now? What island am I looking at, right? Oh, nice island, but which one? So what we ended up with is what you have seen in the video. We basically scale up the texture of that all island mesh, and then we do a small fading to the higher detailed mesh, and this is how you can visualize this kind of transition. Cool. So let's talk about my top 10 HoloLens development recommendations. And first of all, you can be a great 3D developer. You can be amazing, right? You can be the best Unity developer in the room here. But if you don't have a good designer, and if you don't have a good 3D artist, you don't have anything to render. You don't have anything to show, right? And at IdentityMine, we're lucky to have a bunch of very talented designers and also 3D artists who can make great models and also a reasonable triangle count. And I say reasonable because HoloLens is a mobile device, right? So if you take VR devices like the Oculus Rift, the HTC Vive, they have the full computing power of a PC, which is nice, but you're always on the leash, right? You're always connected with a cable. And the nice thing is with the HoloLens, you can just freely walk around with it because computing is all inside the device. But this, of course, also limits the computing power you can put into the device because you cannot expect to have a full-blown desktop graphics card in the thing. It would probably get super hot and burn your user's head, something you want to avoid, I guess. So limited resources, and you need to be careful about computing. And what we noticed is that the HoloLens is mostly fill rate bound. So you can render tens of thousands of triangles without an issue, 50,000 triangles, no problem. But if they're rendered closely, take up a lot of pixels, and you have a heavy pixel shader, then the performance drops super fast. So you run into trouble quite easily. So my recommendation, draw your pixels as easy as possible. So don't use the Unity standard shader, for example. We actually noticed that you can get away with vertex lighting most of the time. So that's just working fine. So very simple pixel shader. And also, it's with every mobile device, right? Avoid overdrawing, avoid stacked meshes so that you don't draw the pixels multiple times, avoid big transparent layers, those kind of things. And then you're good to go with 60 frames per second. Because you need to keep 60 frames per second with the HoloLens. Otherwise, it's dropping to 30 frames. And this means the holograms become unstable. So as you have seen, maybe the holograms are quite stable, even if you walk around. This is super impressive with the HoloLens. They do a very good job with the spatial mapping. But if you're dropping to 30 frames per second, they can become unstable. And this can actually make users sick. They can throw up, they can get headaches and whatnot. So make sure you run with 60 frames per second and optimize a lot, actually. Still, the HoloLens has a quad-core CPU. And you can leverage that. And what we do in HoloFlight, the data fetching, the filtering, and all of that, this is all done on a background thread. So we can keep the UI thread free from that work, and the UI thread can keep up with the rendering loop and doesn't run into those kind of issues. Yeah, you're all familiar, Unity developers, so you're probably good at 3D math as well. But if you just want to get into that, make sure you pick up a good book and learn a bit about linear algebra and those kind of things, because they apply, right? It's a 3D world we're living in, and you have 3D devices, so you have 3D math to compute those kind of things. This is an important one, anchor your holograms. So as you have seen in demo, we created the game object, the container, where I grouped like the plane and the cubes in one. And what I could do, I could apply a world anchor to that container. And this world anchor is an API that is from the HoloLens and mapped into Unity, basically. And this tells the HoloLens runtime on the device to give this object its own coordinate system. And what happens there is that the HoloLens will spend extra time to make it very stable. So once you place your hologram somewhere, add a world anchor to it, so it's very stable. Even if you walk outside the room, get back into it, it will be at the same position. And that's super amazing. And the best part about it, you can actually persist those. So the HoloLens has global storage where you can save those world anchors. And then you can reload them if you relaunch the application. If you're actually also restarting the device, they will also be there. So actually, when I get back home to my office, I will see some holograms in my office. Right? They're still there, even without me. So good stuff, world anchor. Good API, very important, because it's often overseen. Yes, leverage level of detail. So what we do in HoloFlight, we actually, so at a certain distance, we swap those plane models out with a cube. Because you just see a few pixels anyway, and you don't notice that you're just looking at the cube. So you can save some rendering there. But also, what we do in HoloFlight, we make sure that the cube always stays at the same size, even if the user walks further away. So at a certain distance, we swap the plane model to a cube, and then if the user steps further away, we will make sure that he still sees some pixels and knows that there's something going on there. So, but in general, level of detail is always good to save some triangles. Yes, gaze cursor. So the gaze cursor is probably one object the user will see most of the time in your application, right? Because you need to indicate somehow where the user is looking at. So pay attention to the details there and make it very stable. And I say stable because the gazing is based on head rotation, which is in turn provided by the IMU sensor. And like every sensor in the world, the raw data contains noise. And what this means for the gaze cursor, if you would apply the raw data, the gaze cursor would jitter, slightly move all the time, which is not nice, right? It looks like you have Parkinson or something. So you don't want to have your users experience that. So what you can do is you can apply a smoothing algorithm to it. Well, actually, you should do that. And the Holo Toolkit I mentioned, this open source project by Microsoft, actually also has a smoothing algorithm built in. So you can just use that out of the box. We actually don't use it. We developed our own smoothing algorithm because it gave us a bit of better results, less lagging, a bit faster to react, and so on. But regardless what kind of smoothing you use, just make sure you apply some nice smoothing to it and avoid that jittering. Another thing with the gaze cursor is the hand-ready state. So with the device, like I said, it has a bunch of cameras. And if you're wearing that device, and it needs to see your hand in order to trigger the gesture, right? So if I put it on and would do the gesture here, it wouldn't recognize the gesture because it cannot see my hand, right? The hand needs to be in view somehow. It's quite a wide field of view camera up here, but still, if you do it like this, it won't happen. And a lot of users who never use the HoloLens make that mistake, basically, right? So you want to have some kind of indication that the hand is in view, the hand-ready state, if you will. And what the HoloLens start menu does, or most of the HoloLens application, they do this by showing a different gaze cursor. So they show an open gaze cursor, like a ring, if the hand is in view, telling the user, now you can tap, you can interact. Or they show a closed one, like a flat circle, to indicate, I don't see your hand, basically, right? So open circle. But you can come up with even cooler stuff. There might be better ways to actually do that. But anyway, this is a detail you also need to pay attention to, because otherwise it's kind of weird. The user doesn't know what's going on. The user is gazing at something, then tapping, but nothing happens. So that's a good way to indicate it. Yeah, like I said, use transformations, use animations, transition between different states. Be very careful about speed. Don't do too fast. And yeah, test those stuff out. Yeah, so we have a bunch of different HoloLens projects we're building with Unity. And so, of course, we have some reusable scripts in all of those projects. And the naive approach would be to copy those scripts in different folders, right? Which is not very smart, because if you have a bug in one script and you want to fix it, then you have to update all the copies of your script file. So what I did instead is I created a central C# solution where I have all those script files in one central place, and I build a DLL, and then have a post-build step to copy that DLL into all the Unity projects we do. So you can use the Unity assets/plugins folder. You can put a DLL inside there and use our scripts right from the DLL. So one central C# solution with all the reusable scripts, and just create two different DLLs. So actually, the solution contains two different C# projects, one for the editor, because it uses the mono runtime, and one for the actual device, which is UWP.NET Core. And there are also some if-def precompiler directives inside there. And I'm glad that I saw the roadmap right before my talk here, that finally mono runtime is updated, which is probably helping us to remove some of those if-def precompiler directives, because they are usually a pain, right? Anyway, so we have that central C# solution, post-build step to copy the DLLs into the folder. Works out very nice for us to have a good maintainable solution. Yeah, avoid the long deployment cycle. So this is also, like you've seen, it takes quite some time to deploy to the emulator or the device. So what I did here is I wrote a script so that I can simulate the gazing and gestures and all of that stuff like the emulator does, but I can do it already in Unity. So I can launch just the game mode and can try out all of that stuff inside Unity. And I don't have to deploy it every time for every little piece to the emulator or the device. This is like a huge productivity gain. And that's actually one of the first things I wrote when we started with HoloLens development last year. Because you saw how long it takes, the deployment cycle. So you want to avoid that, be smart about it. And we did some custom scripts there. But of course, in the end, you want to deploy it to a real device, right? If you're lucky to have one. The emulator is nice, works well. You can also, try speech recognition and spatial mapping and all of those things. But nothing comes as close to device as a real device. You have the holographic frame size, you have spatial sound, you have a different performance, and so on. Good, we're almost at the end. 4 minutes left. So time for conclusions. Next chapter of computing is happening right now. That's what I'm really sure about. We have all those amazing VR devices, and we have augmented mixed reality devices like the HoloLens. And the HoloLens is really one of its kind. You cannot compare it to anything else that is on the market. It has a spatial mapping, it has this nice holographic, it has those special lenses, this holographic view, if you will. And it's amazing, and I think it will change how we interact with computers. So it's really good when we talk with clients to get all the ideas. There's so much stuff that you can actually do with it. And it's nice And as Unity developers or others, you can build 3D stuff for it. Because you can even do 2D. You can build 2D Universal Windows Platform applications, but they will run in a window, right? But on a 3D device with 3D holograms, you probably want to have some 3D content. So that's good for you. You can all build some cool stuff for HoloLens. You can get the HoloLens SDK with that special Unity build from that location. It's all for free, basically. You can get the HoloLens SDK. It contains the emulator plus the special Unity build, and you can get started right away. There's also a link for the Holo Toolkit, which I mentioned, open source project by Microsoft with a bunch of prefabs, scripts, and so on. And there's also a link to my blog where I will post the slides and the demo, a link to the GitHub where I put on the demo code for the stuff you have just seen. And I also have a write-up for my top 10 development recommendations on that blog post with more details if you want to read those.